So today I want to talk about motors. It was an invention that was created or discovered by Michael Faraday, and it was groundbreaking because he was able to convert electrical energy into mechanical and then eventually show it could work backwards, mechanical energy into electrical. Just like the voltaic pile, it kind of spurred on a lot of inventions afterward because of its usefulness. And also, motors itself hasn't changed much over time. Like the mechanics of it stays the same. Like you have better technology within the motor, but how a motor works in essence is it pretty much the same for the last 100 years. To understand how motors work, we will go back to how a current creates a magnetic field. So in this case, you have a piece of wire, and you have electricity going through that wire, and you create a magnetic field. In this case, it's moving counterclockwise. How can I tell? Well, if you look at the picture, you'll notice that the circular path, the arrow up front is covering the wire, and the arrow in the back is not covering the wire. So imagine if this was the wire. Okay, so in front of the wire, I'm trying to make sure my orientation is correct. My fingers will be pointing this way, and then behind the wire, my fingers will point this way. And you'll notice that behind it, the wire is in front of my fingers. This is counterclockwise. By looking at this wire, I'd like you to try to figure out, is the current moving up or down? And I'll give you guys a few seconds to think about it. Pause if you haven't figured it out. But if you have, the correct answer is up. And I kind of showed it off. So if I grab my wire with my right hand, the only way that my fingers will curl around my pipe is counterclockwise. Now the opposite is true with my next picture. This way you'll notice that it's rotating clockwise, and the only way that my hand could grab this pipe clockwise is if my thumb is down. So that's the right hand rule. Thumb is current, fingers is the magnetic field lines, and the way that you grab the wire is how it's going to determine which way it's going to go. Now, I'll be honest, a wire in a straight line is not very useful, even with current going through it. And the reason is because it's a circular path of a magnetic field. We really want to define north end and a defined south end to kind of get usefulness out of it, or electromagnets. So, like we said last time, what you could do is instead of having a straight wire, you could have it in a loop. So here's a loop, and both sides are going to do the same thing. So this is going to act like a single straight wire, this is going to act like a single straight wire. But what's cool is, as current is moving around in a certain direction, right, for this side, if my thumb is grabbing it, the arrows are pointing this way and going around. On this side is the opposite. Here my thumb was pointing towards me, now my thumb is going to be pointing towards you, and my fingers are going to grab it this way. But what's neat is that even though they're opposites, meaning that this one's going counterclockwise and this one's going clockwise, what's happening is on the inside, no matter where you are in the loop, it's always pointing up. And on the bottom side is always pointing in. So then what we will get is a defined north and a defined south. So electromagnets always are in loops. And the reason is because then you get a north end and then a south end. To kind of emphasize that a little bit more, here's another picture. And you can see that the loops of magnetic field will always point in a certain direction. So that's this far end of this picture is going to be north. The near end of this picture is going to be the south end. So here's another picture of the same thing, a little bit more exaggerated, more loops, probably more voltage and more current, and you get the following thing. And then obviously if you elongate even more, then you'll kind of have more loops, you'll get more of a north end and a south end. So this is kind of what a bar magnet looks like, but it could be long, it could be compressed. Either way, you're going to get a north end and a south end. This is actually really useful because now you have a magnet that turns on and off when you need it to. A permanent magnet, you can't turn it off, so it's always going to get stuck, right? It's going to stick to something or repel something. But this one, I could control when it's going to attract and actually when it's going to repel. And just using that property, you could create a motor. Now, before today, what we're going to do is try to explain a motor. And then another very simple object is your earbuds. Not the wireless ones, but that. And then if we have time, we're going to talk about transformers, which are just, or not transformers, induction chargers, which are really neat. It has a lot of potential to future technologies. first, the motor. So if you watch this, what's really neat is you could totally make this at home. All you need is to have copper wire. And if this copper wire is a little bit different from normal wire, this is called motor wire. And the reason why it's a little bit different is because instead of being coated by like a rubber insulator, it's just coated by varnish. So this person is scraping off the varnish of the loop. So pretty much one end of the varnish is going to be scraped off, and there's going to be a reason for that, which we'll explain. But there he has a loop with varnish scraped off. And what he's going to do, or she, is going to put this loop on top of the permanent magnet and then send current through it. So let me kind of fast forward. So you'll notice right here, here is a battery. The current's going to go from the positive end up through the loop back down to the negative end. And then what's going to create is a magnetic field. And that magnetic field is going to interact with the permanent magnet on the bottom, which is going to create motion. And like I said, normally we make this in the classroom. It's actually quite fun. But yeah, this is a simple motor. It's not very efficient, and we'll kind of explain how we made it better. But it's very, very simple. Same concepts. This is pretty much how it works in a motor. All right, so let's explain it. So this is what he did. He got a bunch of loops, and we know that as current is going through this loop, it's going to create a magnetic field. Okay, so as current is going through this loop, let's say it goes this way, it comes out here. So let's say this is the positive end, the negative end. The current's going to go through, loop around a bunch of times, and come back out. Because of that, if you get your right hand rule, and I grab it with my right hand, the arrow is always going to be pointing towards us. So a dot. So the magnetic field is going to come out at us with a dot. So dot is usually the point of the arrow. If I drew an X, it's the butt of the arrow. Now, that's not the important part. The important part is why he only shaved off the bottom part. And that's kind of quite important when you think about what's going on. So in my next slide, I have the following. So here's my loop. And what I did was I represented one side of the loop as blue, the other side of it as red to represent north and south. And I have a permanent magnet on the bottom, which is always going to be north and south. It will never, ever change. Now, when you look at this, right here, we have this side to be the north end and this side to be the south end. Remember, one property of magnets is that they either attract each other or repel. So the north and north repel each other. So they don't want each other. So you're going to try to push this side this way. The south and south are attracted, or south and north are attracted to each other. So what's going to happen is this is going to go this way. So it's going to rotate around. And then now you have south and north. And it's happy, right? Opposites are closer together. The similar poles are further apart. Now, if this electromagnet was always on, it's going to get stuck because it's happy right here. So it's not going to rotate anymore, and this thing's going to not move. That's not actually a very useful part of it being a magnet. So if we look at the wire on the side, so what I mean by the wire side is I'm going to draw, or at least try to draw, this part right here. So I'm going to represent it as a circle. So here's my wire, a cross section of my wire, and let's say I represent the paint as my pink line. Okay, initially that's how it was, and this person got a knife, but you could also get sandpaper, and they scraped off the bottom. So what was left was just the top side part. So only the bottom is bare, meaning that this part is able to conduct electricity. No insulator. Insulator. So the paint acts like, or the varnish acts like an insulator, so it can't conduct electricity. So now if this is connected to another wire, electricity could flow through the loop. So going back to that other picture, electricity could go through the loop when it's on the bare parts, loop around, and come back out. When it's touching the insulator, so if this thing rotated, it's going to touch and it's not going to conduct electricity anymore. So what's going to happen is over here, remember this thing is rotating around this way. Oh, why isn't my pen working? This way. This thing's rotating around because of the north-north interaction. And as it rotates around, my varnish or paint rotates around. So now my varnish is this orientation, and since there's paint now, it's not in physical contact with my wire anymore because it's now insulated. So now my electromagnet is off. So this north and south interaction won't ever happen and it won't get stuck. So since it had momentum before, this thing's going to continue rotating around until it turns back on again. So in this position, it's still off because now the paint is upside down. Okay. And then in this orientation, it's still off because my paint is this way. But then as it rotates again really close to the vertical position again, it's going to turn back on. So what's going to happen is on, it's going to make it rotate, off, but momentum's going to continue this motion around until it turns back on again. So that's why it circles around. In class, when you make this wrong, what will happen is if you don't do a good job sanding, the loop will get stuck and sometimes it will flutter around because what happens is it turns on and it gets stuck. And then it'll start heating up because once it's stuck, you're technically shorting it out. So as it rotates around, kinetic energy will keep the motion moving once it attracts, but it'll turn back on once it's in this position again. So that's how a motor works. Now, like I said, this is a very simple motor. It doesn't work very well. But what happens is, what happens instead of just having one magnet, let's put in two. And that's what most motors are. So you have more than one arm. Let me see, did I put in the picture? I guess not. Oh, there it is. So most will have more than one arm. So here's kind of something that I took from How Stuff Works. They do a really good job explaining what's going on. So here is something called a brush. And what's really neat about a brush is that this does not move. So right now, let's say this is the positive end of my battery. And this is the negative end of my battery. So the current is going this way. So it's going to go here. It's going to go through my loop. And then what's going to happen is this side's going to be my north and this side's going to be my south. North, again, is repelling each other. It's going to be attracted to it. So as this rotates around, what's going to happen, you'll notice, is a gap. This gap is going to prevent it from being on when the north and south are right here, because then it'll get stuck. Momentum's going to carry it so that the armature, which is the thing that moves around, is going to be here. Now here, if you think about it, well, if it becomes north in this position right here, it's going to fling back, right, once it turns back on again. But what's neat is if you watch how the wiring works. Let me get rid of this. So if I colored this blue and this side yellow, as it rotates, you'll notice the red brushes are always going to be positive or negative, but as it rotates, you'll notice that right now the blue part of my magnet is touching the positive, the yellow wire of my magnet is touching negative, but as it rotates, it's going to flip. So instead of having the wires going positive blue and then yellow negative, it's going to flip. It's going to go positive yellow, blue negative. And what that means is as you change the current direction of my magnet, I'm going to flip my magnet. So here it's going to, as the armature comes here, it's going to turn off. And then as my armature is here, it's going to turn back on again. But instead of north being on this side, it's going to be south on this side and north on this side. So you get that repulsion again, right? This side is going to be attracted to the north. This side is going to be repelled by the similar one. Same thing with the south on the other side. And that's how a motor works. So if you look at this animation or GIF on the left, it's rotating around because it's alternating positive and negative. And that's how a motor works. You turn on the magnets, you turn it off. And then you flip the polarity of it. So it's going to be this motion that's going to go around. This is just having, you can see there's 2 loops of wire or 2 armatures. You could also have 3, 4, or 5. So if you look back to my first picture, way back. Oh, I do not. I guess on my previous lecture, you'll notice like those big motors will have a lot of arms or a lot of loops to it. So every time you're adding a loop, you're adding strength to that motor.